So, hello, welcome to the review videos for Shaughnessy's class. This is Exponents and Logs, Lesson 4. We've talked about exponential equations. In the previous lesson we looked at them where they were of the same base. Now we're going to get out of that. We're going to do ones where there's no common base. And how do you do that? So getting going, keeping in mind, show up to class because there's going to be more examples. That sort of jazz. Now, first off here, to do them without a common base, I need to teach you about the connection between the two. Now, the connection between the two is that they're inverses. We kind of mentioned that before. But because they're related, because they're inverses, an exponential equation has a logarithmic equation form. Okay? It just looks different, but you've transformed it. I mean, my kids are really big into transformers, more than meets the eye, that sort of thing. Okay? It's the same guy. It's Optimus Prime, whether he's standing there as a robot or standing there as a truck, or I guess not standing, but you know what I mean. It's the same thing. Exponential equations and logarithmic equations have multiple forms. Now the rule, the conversion, is this. Okay? Basically, if you have an exponential form, a times b, or a to the power of b equals c, that's an exponential form. Okay, and you may be happy with that. That may be the exponential form. There is a logarithmic form that corresponds, okay? And the corresponding logarithmic form, you have log, the log of the old base. So if the base was a on the exponent, the base is a on the log. So log base a of, now in this case here, the a was paired with the b, now the a is paired with the c, so you've switched it around. You're trying to do the opposite operation. Log base a of c, and that equals b. These two equations, whether they look the same or not, they are entirely different. And the logarithm is doing a logarithm to a particular base. Just like when you're calculating an exponent, there is a base to it, and that base has to stay constant. When we're working with a log, there's a base to it, and it has to stay constant. This is the logarithmic form. Both of these equations are equivalent to each other. They're fine. Okay? You just have to remember that the base stays the base, and the base was with something, it's now with something else. Okay? Ditto here. The base was the base, it was with something, now it's with something else in the other form. Okay? So you go through that. Okay? And so once that's done, you get this idea of convert to logarithmic form, and I can give you an equation. Whether or not we have all the pieces is irrelevant. If I say 2 to the 5th equals 32, okay? Which is true. 2 to the 5th is 32. If I say 2 to the 5th is 32, written as log form, the base was 2. So it's going to be log base 2 of, it was with the 5, now it's with the 32, and that equals 5. Now, we have all the pieces there. Excuse me. We have all the pieces there, so it's not really helpful there. But when I'm looking at like an exponential equation, when I'm looking at something like e.g. 27 to the power of x equals 13, and I need to know what x is, I can't figure it out there. It's a guessing thing, and I don't know what works or whatever, and it's going to be a weird decimal, and how accurate do I get? Whereas now I could say this is the log base 27 of 13, and that's going to equal x. And now I know what x is going to be, so I can solve that exponential equation. You can do any of these conversions you want. It's still the same idea. If I look at one like this, e.g. 2x cubed equals y, and I want to convert it to logarithmic form, it's not quite exponent all by itself. I'm going to move that 2 over and say that x cubed equals half of y, or y over 2. And then from there, converting it to log form, okay, log, the base was x, so log base x of y over 2, okay, equals 3. And so I can do that conversion. I can go with it from there. Now the idea is you can also go backwards as well, okay? So convert the following to exponential form. So if I gave you something like this, e.g., the log base 2 of x equals 7, okay? I'm just using that conversion. The base of this log was 2, so the base of the exponent has to be 2. So it's going to be 2 to the power of something. On this side here, the 2 is with the x, so now it's going to be with something else. 2 to the 7th equals x. This is the exponential form for that equation. This one I can figure out again. Okay, sometimes it's not helpful, sometimes it is. Okay, I can give you ones like this, e.g. 4 log base 7 of x equals z. Okay, so 4 log base 7 of x equals z. Well, this 4 is still on the wrong side, so I can say it's log base 7 of x equals z over 4. And now I can do the conversion. 7 was the base of the log, it's the base of the exponent. 7 to the power of z over 4 equals x. And there it is as an exponential form. I'm just swapping forms back and forth. Now keeping in mind, it doesn't matter which form you use, they are both the same. I'm just converting, I'm transforming, okay? Once you're comfortable with that idea, the key is this. Sometimes you want exponential form, sometimes you want log form. The only way to realize is which can you calculate. Your calculator can do both, but you want the one with only numbers. You can calculate those. Now, certain logs are easy. Log base b of b to some power. Log base b of b to some power is the whatever the power is. So this means I can do this, e.g. Oops, I guess the e.g. is there. Log base 5 of 5. Okay. I look at this, log base 5 of 5. Well, that is 5 to the 1. Log base 5 of 5, the exponent is 1, that's going to equal 1. And that's all you have to do. If I give you something like this, e.g., the log base 7 of 49. Okay. At first glance, it looks like it's hiding, but log base 7 of 49, that is the log base 7 of 7 squared. Based on this rule, the exponent was 2, so the log base 7 of 7 squared is 2. Okay, you're done. If it's a power, you can just do it. The log base 2 of 128. I don't know what it is, but I know 128 is some power, so I figured it out. 2, 4, 8, 16, 32, 64, 128. It's 2 to the 7th. So I'm going to get the log base 2 of 2 to the 7th. Okay? By this rule, that's going to be 7. Done. It's that simple. Okay? If, and here's the issue, if the base of the log is completely unrelated, okay, if the base of the log is completely unrelated, you need the calculator. Okay? We used to use something called log tables. I have them somewhere. I don't use them anymore. The calculator is way more efficient. If the base of the log is not shown, it's 10. That's just kind of a rule. But if the base is completely unrelated to the number, we have to use the calculator. Now, how do you do that? Okay, here's an example. E.g., log base 3 of 13. Okay. 13 isn't a power of 3. So now it depends on the calculator you have. Okay? I have a TI-84 Plus, and I've updated mine. If yours isn't updated, but you have a TI-84, I can update it. Okay? If you have a TI-83, I can't update it. If you have an 84, you can turn it on, and you're used to using the shift button or the second button. In this case, if I do alpha, it's the green one. If I do alpha and push one of these buttons here, specifically the second one, then it gives me another menu. And along with this menu is hidden. And in the 83, it's not there. In an unupdated 84, it's not there. Okay? There's log base. Now the reason I bring that up is because now if I needed to figure out the log base 3, I can type it in. That's 13. Okay? And I can get the answer. 2.334717519. I'm just going to write 2.33. Okay? If you do not have that updated operating system, either because you don't have a calculator that can do it, or you don't want it. Okay, you end up using this button here. Now here's log. Okay, it's right beside the 7. Log. Okay, you can use that button, and every time I get log, that's the button I'm pushing. So I want to type the log base 3 of 13. Well, if I hit log on the calculator, it doesn't give me an option for base. So that's where that note came in. If the base of the log, not log, if the base of the log is not shown, the base is 10. This is a base 10 log. I want a base 3 log. So if you don't have the right operating system, I'm sorry, but the only way you can do that is you've got to type the log of 13, close the bracket, divided by the log of 3. Okay? And I could explain where that comes from, and I will if you're curious. But that's what you have to do if you don't have the calculator that does logs to different bases. In that case, you get 2.33 again. Okay? Keep in mind, if I just type the log of 13 and ignore the base, I get the wrong answer. So that's no good. Okay? The calculator, just purely by convention, there's no reason why, I guess. Probably memory restrictions back in the day. Calculators use base 10 logs, and that's all they did. When I was in high school, that's all they did, base 10 logs. Now we have the option, remember, of pushing alpha and the window. And it brings up this menu, so I can get log base, and then I can type log base 3 of 13, and enter, and it's done. Okay? It's not important enough for you to go out and buy a new calculator. Please don't go out and buy a new calculator if that's what you think. Okay, if you like, oh, I really want that and I can't have it, so what? We'll do it a different way. We'll get there, okay? So it's the same thing. It's not important enough. Okay? But it allows you to go through and do logs to different bases. If I do another example like this, and I do log base 7 of 100, okay, that's a log to different bases. Okay, so I can go into my calculator, I can go alpha, window, log base 7 of 100, and I type that in, hit enter, 2.36. It's just coincidence, they're both 2.3s. Okay, so you get 2.37, 366, so 37, and so on and so forth. Keeping in mind that if I don't write the base, it is 1. So if I do the log of 90, okay, if I want the log of 90, you can ask yourself, what's the base? It's base 10. The nice part is these ones, it doesn't matter which model, just use this log button. Okay, this log button does log base 10s, so I could just type log of 90, and it's the same thing. Okay, 1.95. Because base 10 is already in the calculator, I don't have to use anything special, so it ends up being 1.95, and so on and so forth. Okay, now you can round it to whatever decimal you want, but that's key. Okay, if you have an updatable calculator, but don't have it updated and want it updated, come see me, I can do it for you. Okay? Along with this then, once you're comfortable with logs, we get to this whole idea of estimating the value of logs. This is pretty complicated, but at the same point in time, it's not really hard. Okay? Estimating the value of logs. And I said estimate the value of log base 2 of 25. Okay, now I could go type it into the calculator, figure it out. Doesn't matter. Let's say I'm estimating it. Now I'm looking at this, and I'm thinking, I don't know anything. I don't know this. I don't know what log base 2 of 25 is. But the thing I remember from logs is the whole idea that the log base b of b to the n equaled n. Okay, that was a rule from before. Okay, if I have the log base b of b to the n, that equaled n. So here I could have the log base 2 of 2 to the 4th, or 16. And that's going to equal 4. And then I could have the log base 2 of 2 to the 5th, or 32. And that's equal 5. and I could figure that out. I could prove it. Go type it in if you don't believe me. But using those now, I can at least get some approximation for the log base 2 of 25. Because I know that the log base 2 of 16 is 4. And I know the log base 2 of 32 is 5. It's got to be between 4 and 5. Now, then I can ask myself, is 25 closer to 16, or is 25 closer to 32? It's 9 away from 16, it's 7 away from 32. So it's a little bit closer to 32. So it's going to be a little bit closer to 5. So there, my estimate is between 4 and 5. And a bit closer to 5 than 4. So it's a bit closer 5 than it is to 4. So what am I going to do? I need a little bit closer. 4.5 is directly halfway. I got to be a little bit closer. So I'm going to guess 4.6. Okay? That's going to be my estimate. Okay? I know it's not 4.3 because it's got to be closer to 5 than it is to 4. I know 4.1 doesn't work. I know 4.5 doesn't work because it's not dead on halfway between. I'm guessing about 4.6. Now you could go figure that out, but that's what my guess is going to be. Okay? So continuing on. Connecting to exponential equations. I don't know why this says exponentially quotations. Exponential equations. Okay? So connecting to exponential equations. We can easily solve equations like this, and you could. Okay, this was ones we did before. 2 to the power of x plus 6 equals 8 to the x. Because those were common powers. I recognized they were powers of 2, so I get 2 to the power of x plus 6 equaled something to the power of x. 8 was 2 cubed. And we did this the other day. So once I recognize that's 2 cubed, then I work this out. I get 2 to the power of x plus 6 equals 2 to the power of 3x. Ignoring that, I'm going to get x plus 6 equals 3x. Moving the 6 over, I'm going to get 6 equals 2x. Divide by 2, I'm going to get x equals 3. There's my solution. That one we could do. That we did before. Okay, and if they're common bases, they're all good. Okay. Now the key thing is, what if it's not a common power? Because it's not always a nice number. And you're trying to look for applications. You're trying to look for things where, the science or whatever can be used or dealt with doing the science. If I give you an equation like this, 3 to the power of x equals 14, there is no common power. It's just not possible. So in that case, there's a variety of things you can do. In my opinion, the easiest is, okay, well, that's an exponential equation, and I can't do anything with it. But I'm going to try converting it to a logarithmic equation, because every exponential equation has a logarithmic form. So converting this to a logarithmic form, it's going to be log, the base was 3, of, was with the x, now it's with the 14, equals x. X is what I'm trying to find. I know x is the log base 3 of 14. That's just a number. Okay, I don't know what that number is off by heart. I could estimate it using what we did above, but nonetheless, log base 3 of 14 equals x. And I can figure that out by typing it into the calculator. Okay, and it'll give me a decimal. It's not exact. This is exact. Okay, just like when we had quadratics, this is exact. I'm going to write that here. This is exact. Okay. Okay, that is exact. If I don't need the exact or I want a decimal approximation, alpha, window, log base 3 of 14 equals 2.402. So this is about 2.402. Dot, dot, dot. Okay? And so I can solve these exponential equations. And that's what I'm doing. I'm using the ability to convert from exponent to log form in order to solve equations. Okay? Now, you could leave it as exact form. In 30-1, for sure, everything would be in exact form. In 30-2, we don't panic about it too much, but that's the general gist, okay? So when you're looking at these exponents and you're trying to figure out what you can do, okay, you just solve a whole variety of things. So if I look at some more examples, okay? Oh, sorry, correction. I think I've got a little bit more to tell you. Okay, so if they're not the common base. Okay. Steps. Look for a common base. If there is a common base, do it. Okay, and just do it the way we did it before. If there is no common base, simplify it so you got an exponent on one side, a number on the other, and convert to a logarithmic form. Then once that's done, you just solve what's left. So I can do example after example after example, and I'm just kind of making them up as I go. So I apologize if they don't work out too terribly nicely. But I could do example 17 equals 4 to the power of x plus 1. Okay? So in this case here, I can't solve it, can't find a common base, so what I'm going to do is I'm going to do the conversion. This becomes the log base 4 of 17 equals x plus 1. Okay? Trying to solve for x, this plus 1 is in the way, so I'm going to subtract it. So I'm going to get that x equals the log base 4 of 17 minus 1. Okay? And that's what it is. That's its exact form. I can go through and look at it in here. So it's going to be alpha window, the log base 4 of 17 minus 1. That's 1.04. Okay? Dot, dot, dot. Okay? That's how this is done. Okay? It's the same idea all the way through. E.g., okay? If I give you 96 equals 5 to the power of 2x plus 3. Okay. I say, well, there's no common power. I look there. Always look for the common power. If there is a common power, use it. It's quicker. It's easier. Okay. But all the examples I'm doing here are not. So then I'm going to convert to log form. It's going to be log base 5 of 96. It's going to equal 2x plus 3. Subtract the 3, I'm going to get the log base 5 of 96 minus the 3 equals 2x. Using algebra, I'm solving for x, I need to get rid of the 2. I'm going to divide by 2. So what I'm going to get, and I'm moving the x to the left side just for space, okay? It was the log base 5 of 96 minus 3, and you're dividing all of it by 2. There's the exact form. In your calculator, you go type that in. Okay? So, same as before, alpha there, log base 5 of 96 minus 3. And that's the number I'm going to divide by 2. And I get x is negative 0.82. Okay? 0.82. Okay, dot, dot, dot. And it goes from there. You may be wondering why I didn't type it all in one go. It's just a danger with the brackets. You'd have to remember to put bracket, the log base 5 of 96. Subtract 3 from that, then close the bracket. All of that is divided by 2. Okay, if you don't do that, you will get the wrong answer. Okay? And that gives you the same thing as the negative 0.82. Okay, so on and so forth. That's how this is done. Okay, you can go through and look at other examples. Now, to make this a little bit harder, what about one like this? Okay, if I give you 75 equals 5 times 3 to the power of x plus 1. So, whatever, I'll just leave it at that. This one here. There's a coefficient in front. And with this coefficient in front, I've got to deal with the coefficient first. So I'm going to divide by the 5. So 75 divided by 5. And I go and figure that out. 75 divided by 5 is 15. 15 equals 3 to the power of x plus 1. I need you to understand that it's coincidence, the fact that the 5 plus 3, or 5 times 3 would have been 15, and all of a sudden I've got 15. That's coincidence. It's just the numbers that were randomly chosen. Okay? From there, now that I've got this Stille coefficient out of the way, now I can convert it to log form. So if I convert this to log form, it's going to be the log base 3 of, it was paired with that exponent, now it's 15, and that's got to equal x plus 1. Subtract the 1, I'm going to get the log base 3 of 15 minus 1 equals x. There's my answer, exact form. If I go type that into the calculator, I can get the decimal. Okay. So alpha, window, log base 3 of 15, okay, and then minus 1, and you get that it's 1.64973521. It goes on for a while. So I'm just going to say it's 1.46, sorry. Okay, and there you go. That's solving the exponential equations. Okay, you can do it with the coefficient in front, or you can do it without the coefficient in front. We've done a lot of things today. Okay. Now going back to the front of my lesson, I don't usually do this, but I really quickly want to do this because you did a lot of things in this lesson. Okay. One of the things you did is express a log as an exponent and vice versa. That conversion rule, okay, one to the other. You learned how to evaluate log base a of b when b is a power of a, okay, so when the powers are the same. So we can do that. We learned to evaluate log base a of b with technology, typing it into the calculator, going from there. Then you were solving equations. Sometimes there was a coefficient, sometimes there wasn't, okay? But so on and so forth. You've got the coefficient idea. The coefficient has to be divided off first. They don't go together. It's because of bedmass, the order of operations. You'd have to do the exponent, which has the x in it. You'd have to do that exponent before you could do the multiplication. So that coefficient can't be multiplied in. You have to divide it to the other side. Okay? So you're able to do all sorts of these things by conversion. Lots of stuff today. You are going to get some extra time for homework, but lots of stuff today. Keep in mind that in the class there would have been a lot more examples. Hope that makes sense, and otherwise have a great day.